This video examines the boron carbide paradox, exploring its unique microstructure, failure mechanisms, and potential next-generation solutions for high-performance applications. Boron carbide presents a paradox. Despite its extreme hardness and low density, it suffers from catastrophic strength loss under dynamic stress due to pressure-induced amorphization. The material's performance is governed by its rhombohedral lattice and stoichiometry. Chain vacancies and atomic composition dictate both its electronic response and pressure stability. Microstructure is key to performance. While porosity degrades strength, twin defects can hinder shear band formation, though they may also nucleate amorphization if not precisely calibrated. Carbothermal reduction is common due to its scalability, but boron volatility often leads to stoichiometry drift, which can compromise the quality needed for high-performance use. Spark plasma sintering, or SPS, enables rapid kinetics and high density, helping to preserve nanostructures that might be lost during traditional hot pressing. Additive manufacturing allows for complex geometries, but currently faces limitations with as-printed porosity. Post-processing is required to reach the density thresholds needed for ballistic utility. Ultimately, boron carbide offers unmatched specific strength, yet its dynamic utility is capped by amorphization. Performance relies on selecting the right fabrication method for the application. During ballistic events, stresses above 25 gigapascals fracture the boron 12 cages. This leads to the formation of amorphous bands and a sudden, catastrophic loss of strength. These amorphized zones are permanent, creating weak points in the material. Subsequent impacts can exploit this damage, further reducing the overall resistance of the armor. Environmental utility is also constrained. At temperatures above 400 degrees Celsius, oxidation occurs as boron trioxide volatilizes, preventing effective surface passivation. To overcome these limitations, lightweight armor systems often pair boron carbide with composite backing to absorb residual energy and mitigate the effects of brittle failure. For nuclear applications, boron carbide requires specific enrichment, demanding at least 80% boron-10 and ultra-high chemical purity to function effectively in control rods. One solution to the amorphization issue is the use of boron carbide silicon carbide composites, which can suppress shear band propagation and improve multi-hit performance. In summary, while processing technologies like additive manufacturing provide new design freedoms, balancing complexity, density, and material stability remains the primary challenge for the future of boron carbide. Advanced multi-scale modeling now predicts boron carbide failure by linking quantum-level simulations of icosahedra fracture to macro-scale ballistic performance, helping us understand how twin confinement narrows shear bands. By using DFT and molecular dynamics, researchers can now simulate nanosecond scale dynamics, capturing how amorphous bands nucleate at twin boundaries under high-stress conditions. Looking at fabrication trade-offs, we see that while SPS preserves critical nanostructures, it remains a lab-scale process, highlighting the need to bridge the gap between small-scale purity and large-scale manufacturing. Machine learning interatomic potentials, or MLIPs, are accelerating alloy discovery by bridging the gap between quantum electronic structures and MD-scale shock response, enabling new inverse design cycles. Graded architectures are a key breakthrough for resolving the paradox. By transitioning from a hard boron carbide strike face to a tough composite backing, we can effectively suppress harmful shear band propagation. The future research roadmap prioritizes amorphization mitigation. By converging on advanced synthesis techniques like additive manufacturing, we can develop next-generation armor capable of superior multi-hit performance.